In this section, we're going to look at vector algebra. Vector algebra. We're going to see how to express a vector in terms of two perpendicular unit vectors or orthogonal unit vectors. So let me start by defining a unit vector. A unit vector is simply a vector whose magnitude is 1. A unit vector is a vector whose magnitude is 1. Magnitude is 1. That's what a unit vector is. Now, if you want to find a unit vector in the direction of an arbitrary vector A, all you do is divide the vector by the magnitude of the vector, okay? So let's say this is a unit vector in the direction of vector A, then EA, this unit vector in the direction of A, is simply the vector A divided by the magnitude of A, okay? So if this is vector A over here, this vector whose magnitude is 1 is what we call EA. So EA is a unit vector of magnitude 1 in the direction of A, okay? But we're mainly interested in Cartesian unit vectors in this section. Cartesian unit vectors. These are unit vectors in the direction of the x-axis and the y-axis, okay? So let's say we have this coordinate system over here. This is the x-axis, the y-axis. The unit vector in the direction of the x-axis is called the I unit vector, and the direction in the direction of the positive y-axis is called the J unit vectors. This I is a unit vector whose magnitude is 1 in the direction of the x-axis, and J is a unit vector whose magnitude is 1 in the direction of the y-axis, okay? So let's take an arbitrary vector over here. Let's say this vector A is AX in the direction in this direction over here. Let's say this is AX. So this I unit vector is AX divided by its magnitude AX, okay? So in this direction is going to be positive, all right? So that tells you this vector in the direction of the x-axis is simply its component in the I direction, okay? And then let's say we have this vector AY over here, okay? So the unit vector J is simply this vector AY in the direction of the y-axis divided by its magnitude, which in this case is in the direction of positive y-axis is positive. So we have AY equals AY in the J direction. So a vector in the direction of the y-axis can be written as its magnitude in the direction of J, okay? Now suppose we have an arbitrary vector A like this. You see, this could be written as the sum of a component in the horizontal direction and another component in the vertical direction, like this, okay? These are joint tail to head, so we can say A equals AX plus AY, okay? So using these representations, then we can write this vector to be AX in the I direction plus AY in the J direction. So you see, using the unit vectors I and J, a vector can be written in this form. Its X component in the I direction plus its Y component in the J direction, okay? We can write also in terms of polar coordinates. You see, if this is A, this is AX, this is AY, as you've seen before, AX equals A times cosine of theta, and AY equals A times the sine of theta, okay? So this vector can also be written as A equals the magnitude times cosine of the angle in the I direction plus A times the sine theta in the j direction. So this is the ij representation of the vector in terms of the magnitude and direction of the vector. But I might add over here, this is provided theta is the default angle, that is angle measured from the positive x-axis. Okay, this is provided theta is the default angle, the default angle. If you remember, that means angle measured with respect to east or positive x-axis, measured with respect to the positive x-axis, okay, or east, you can say. All right, so if you use the angle measured with respect to positive x-axis, this formula will give you the right sign for the x component and y component. So this is the ij representation of a vector. Now let's look at examples. Example, suppose you have the following vector. Let's say a equals let's say 10 meters 45 degree, maybe south of west. All right, and the question is expressed in the ij notation. Okay, express the vector in the ij notation, okay, so we'll need the magnitude and the direction of the default angle. Obviously the magnitude for this vector a is 10 meters. The direction, we're told it is 45 degrees south of west. This is west, okay, in the coordinate plane. This is west, this is east, this is north, this is south. Okay, so this means south, 45 degrees south of west. So this is the angle we're talking about. Okay, so this is our vector, and then of course it divides in 10 parts. All right, okay, so the angle we need is the default angle, which is this one. Okay, this one is 45 degree, so the angle we need is 180 degrees plus 45 degrees. That's the default angle, 225 degrees. Okay, so in the ij representation, we can write a as a cosine of theta in the I direction plus a the sine of theta in the j direction. Okay, so this will be 10 times cosine of 225 degrees in the I direction plus 10 the sine of 225 in the j direction. Okay, cosine of 225 degrees is approximately negative 0.7, so we get this would be negative 7 in the I direction. The same thing about sine 225 degrees, it is approximately negative 7. It will be negative 7 in the j direction. Okay, so this would be the representation of the vector in the ij notation. Okay, so these are the components. This is 7 this way, 7 west, 7 down. That's what this means. All right, so if you know the magnitude and direction, you can use this formula to express a vector in terms of the ij unit vectors. Okay, how about if you know a vector in the form of ij and you're trying to find the magnitude and direction? Okay, that is if a equals ax in the I direction, ay in the j direction, and interested in the magnitude and the direction, then of course we have the x and y components, so the magnitude would be given from Pythagorean theorem. Okay, and the direction of course would be tan inverse the y component divided by the x component. And remember, you would add 180 degrees, if ax is less than 0. All right, so to go from a vector written in the ij notation to magnetic direction. We have already discussed this formulas. You can use these formulas. Okay, so let's see example. Let's say if a equals, let's say, -3 in the I direction plus 4 in the J direction. Let's say calculate the magnitude and direction of the vector and direction of the vector. All right, so what we have is, this is the x component. Ax is -3, ay is 4. Okay, now a question mark, theta question mark. For a, we just use Pythagorean theorem, that is ax squared plus ay squared. Okay, that will be square root of -3 squared plus 4 squared, which is 5. Okay, and then theta is tan inverse of the y divided by -3. Now remember, if this is negative, we have to add 180 degrees. Okay, the calculator will give you -53 degrees for this one, and then of course plus 180 degrees, so that gives you 127 degrees. Okay, so you see this vector is this vector. It has a negative x over here, -3, but a positive y over here, which is 4. So this is the vector we're talking about. Okay, so this is the angle 127 degrees. All right, okay, so next we're going to see how we operate with vectors written in the ij notation. Okay, operating with vectors in the ij notation. Expressing a vector in the ij notation, it makes it much easier to operate with vectors, that is addition, subtraction, multiplication, and so on. Okay, because if a vector is written in the ij notation, then you can treat it like any algebraic expression. Okay, so the general rule is treat vectors in the ij notation like any other algebraic expression, of course putting in consideration that I and j are independent, with I and j as independent terms. Okay, so what this means is you can add only I terms together and j terms together. You cannot add an I term and j term. You cannot combine I term and j term together. You can only combine i's together and j's together. Okay, as far as you treat I and j as independent, you can treat vectors written in the ij notation just like any other algebraic expressions, like x and y. You see, when you're adding terms involving x and y, you add the x's together and the y's together. You don't combine them together. Okay, so let's just demonstrate this by means of some examples. For example, let's say a is, let's say, 2 in the I plus 3 in the j. Let's say b is maybe -3 in the I plus 4 in the j. Maybe c is, let's say, just 2 in the j. Okay, so let's try to evaluate the following expressions. Let's say we want to find 3a. Okay, so simply multiply 2i plus 3j. Okay, so you distribute this, simply 3 times 2 you get 6i, and then 3 times 3 you get 9j. Okay, so you treat it like any algebraic expressions like x and y. Let's say this was x and y, you'll say you multiply the coefficient of x with this one, the coefficient with this one, that's it. Okay, so when you multiply numbers, you just multiply the coefficients of I and j. How about, let's say we want to add, let's say a plus b. Okay, so we have 2 in the I plus 3 in the j plus b, negative 3 in the I plus 4 in the j. Okay, now remember, you can add only i's and j's and j's together. You cannot combine both of them. So we can write this as 2i minus 3i, that's this term and this term over here, and then we can combine these two together, 3j and 4j. Okay, so we add j's with j's, i's with i's, so this gives us negative I plus 7j. Okay, now let's try to do this. Maybe 2a minus 3b, let's say plus 2c. all right, so we'll just treat them like any algebraic expressions with I and j independent. So this would be 2 times 2i plus 3j, okay, that's a, minus 3 times negative 3i plus 4j, okay, and then plus 2 times 2 in the j, that's c. Okay, so first we expand the multiplications by constants. So we have 4i plus 6j, then minus 3 times minus 3 is 9, 9 in the I, minus 3 times 4 is negative 12, negative 12 in the j, plus 4 in the j. Okay, so we're gonna add the i's together and the j's together. So you got 4 i's over here, 9i over here, that's all we have. So you get 13 in the I, and then for the j, I have 6 over here, I have minus 12 over here, that gives me negative 6, and the negative 6 plus 4 gives me negative 2. Okay, so it will be j. All right, so you see, when vectors are expressed in the ij notation, addition and subtraction becomes much easier. Okay, you just treat them like any algebraic expressions, and with I and j independent. Okay, so now we're going to look at products of vectors. Okay, products of vectors. There are two kinds of vector product. Even in normal algebra, there are two meanings of multiplication. For example, let's say one of the meaning is one-dimensional meaning. Let's say the length of this one is 1 meter. Okay, if you multiply it by 2, you just get another length twice the length of this one, right? So this is the one-dimensional meaning of a product. If you multiply it, you just get you just change the length of the object. But there is another meaning of multiplication. Take a rectangle. Okay, now let's say this is 2 units in the vertical direction, let's say it's 3 units in this direction. What does the product of this gives you? It gives you the area. Okay, so this is the area interpretation of product. So we have two kinds of definitions of a product multiplication. This is the one-dimensional meaning, which just makes it longer or shorter. But then we have the area interpretation of multiplication. That is, when multiplying something, two quantities that are perpendicular to each other, you get the area interpretation. Okay, so because of that, we're going to have two kinds of products. We have two kinds of vector products. Vector products. They're called the dot product and cross product. Dot and cross product. Okay, so we're going to look at the dot product first. The dot product. This is the scalar interpretation of product. Okay, now let's say we're trying to find this kind of product between these two vectors. Okay, let's say this is A, this is vector A, this is vector B. Okay, the dot product of these two vectors is defined as follows. You take the projection of this vector on this the projection of this vector over here. Let's say this is theta. So this projection is going to be b times cosine of theta. Okay, you multiply that with the magnitude of A, that gives you dot product. Okay, so dot product is written as A dot B. Okay, is defined to be, you take the projection of this vector on this vector, and then you multiply that by the magnitude of the vector. Okay, you multiply this one and this one over here. So we have the following. You take the projection on the vector A, b cosine of theta, times A. That's what you call the dot product. So we have the following definition for dot product. This is A times B times the cosine of theta. I'll say this is A dot B. Okay? Maybe let me write it again. A dot B equals AB times cosine of theta. So this is the definition of what we call the dot product of two vectors. So remember, A represents magnitude of A, okay? B represents magnitude of B, and theta is angle between A and B. This is angle between A and B. Okay, so dot product is scalar, which means it's just a number. Okay, it doesn't have directional properties. Okay, so dot product, it can be positive, negative, or zero depending on the value of the angle. Okay, if the angle is acute, this will be positive. Remember, these are magnitudes, they're always positive, but this could be positive, negative, or zero depending on the angle. If this angle is acute, that's less than 90 degrees, the cosine will be zero, you'll get a positive dot product. If this angle is 90 degrees, cosine of 90 is zero, so you get zero. Okay, that is, if it's vertical over here, doesn't have projection on in the direction of A. And if this is obtuse, that's greater than 180, then cosine of theta will be negative, you'll get a negative dot product. So dot product is a scalar quantity. It doesn't have directional properties, and it can be positive, negative, or zero depending on the angle, right? So let's consider an example. Let's say example, find, let's say A dot B. Let's say if A is, let's say 10 meters, maybe let's say 30 degrees, 30 degree north of east, let's say of east, and let's say B is maybe 2 meters and let's say 30 degree west of north. Okay, so we have the following two vectors. We get this vector which makes 30 degrees, that's north of east, okay, and this angle is 30 degrees, its magnitude is 10. And then we have another vector that makes 30 degrees west of north. Okay, this is 30 over here. All right, and its length is 20. Okay, so what we have is A, the magnitude is 10, B, the magnitude is 20. Okay, now theta is this angle over here. Okay, so the 30, this is 60 over here. So the angle is 60 plus 30. We're looking at the angle between these two. So the angle between them is this angle over here, 60, which is 90 minus 30, and then plus this angle 30 over here. Okay, so that is 90 degree. Okay, so let's calculate A dot B. A dot B would be magnitude of A times magnitude of B times cosine of 90 degree. And cosine of 90 degree is 0. So the dot product between two vectors would be 0. Okay, because they're perpendicular to each other. If they are perpendicular to each other, they don't have components in the direction of the other vector. Okay, so this is an example for dot product when the two vectors are given in terms of polar coordinates. Okay, that is magnitude and direction. All right, now we're going to look the dot product. But before that, I think let me look at some properties. So we just saw over here, if two vectors are perpendicular to each other, then the dot product is 0. Some properties. Let's look at some properties. If A is perpendicular to B, okay, as we just saw over here, A dot B is 0 because the angle between them is 0. Okay, you will have AB cosine of 90, and that would be 0. Okay, A dot B would be 0 if A is perpendicular to B. Another property is if you dot a vector with itself, what do you get? Okay, so the angle between two identical vectors is 0, right? So it'll be A times cosine of 0, right? Cosine of 0 is 1, so you just get A squared, right? So A dot A is simply A squared. Okay, so that's one property. Another property is you can distribute dot product over addition. If you've got A dot B plus C, then you can distribute it. This equals A dot B plus A dot C. So that means dot product is distributive over addition. You can just treat it like a normal multiplication if you've got something like this. Okay. All right, and dot product is commutative. Okay, the order doesn't matter. So if you do A dot B, that's the same as B dot A. We can see that's not the case for the other type product, but for this one, like normal multiplication, it is commutative. If you change the orders, the meaning of the dot product doesn't change. Okay, so these are some properties of dot product. Now let's see dot product in terms of I and J unit vectors. Well, dot product, let's say this is of vectors, let's say vectors expressed in terms of I and J unit vectors. Okay, so let's see how we do that. We want to see how to obtain the dot product of vectors expressed in the IJ notation. Okay, first we're going to look at the dot product between the unit vectors. Okay, so let's look at I dot I. Okay, so the angle of them is 0, the magnitude of both of them is 1, so you've got 1 times cosine of 0. Okay, that's 1 times 1 times 1 equals 1. So generally, if you dot a unit vector by itself plus J dot J, let's make it more general. K is a unit vector in the direction of Z, so let's say K dot K. I know I haven't mentioned K before, but I is the direction of x-axis, J is in the direction of the y-axis, and K is in the direction of the z-axis. Okay, I, J, K, like this. All right, so this is in the direction of z-axis, x-axis, and y-axis. So these are all equal to 1. So if you dot a vector by itself, you get 1. How about if you dot a unit vector with another one? Let's say let's dot I with J. Okay, now the angle between the I and J is 90 degrees. Okay, so this gives me 1 times cosine of 90. Okay, you get 0. So if you dot two different unit vectors, you always get a 0. So you've got A dot J is the same as A I dot k is the same as j dot k equals 0. Okay, so when you do dot product with unit vectors, remember that if you dot a unit vector by itself, you get 1. If you dot a unit vector with another unit vector, you get 0 because they are perpendicular to each other. Okay, now before I proceed, let's tell a little bit about the three-dimensional vector. For three-dimensional vector, you've got 3 vectors like this. Okay, so you will write a vector like this: ax in the I plus ay in the j plus az in the k. Okay, and the magnitude would be simply square root of ax squared plus ay squared plus az squared. All right, the magnitude of this kind of vector is square root of ax squared plus ay squared plus az squared. Okay, for example, let's say you have something like this. Let's say this is the I direction over here, so you will have the x component over here. Let's say it's the j part. You have the ay component over here. Now this one over here would be the square root of ax squared plus y squared. But then if you have a z component, az, okay, so this is, you have another right angle triangle over here. Okay, so you get the square root of ax squared plus ay squared, square root of that, plus az squared. That's what you get over here. Okay, so for a three-dimensional vector, you can use this formula to calculate the magnitude of a three-dimensional vector. All right, now with that, let's see how we can obtain dot product between 2 vectors expressed in terms of ij notation. Okay, now suppose we have the following vectors: a is ax in the I plus ay in the j plus az in the k. Let's say b is bx in the I plus by in the j plus bz in the k. Okay, so now let's do a dot b. A dot b would be ax in the I plus ay in the j plus az in the k, dotted with bx in the I plus by in the j plus bz in the k. Okay, now we're going to use the distributive property. Okay, first we dot this with this one, this with this one, this with this one. Okay, so this equals ax in the I dotted with b, which is bx in the I plus by in the j plus bz in the k. Okay, plus then we dot this one, ay in the j dotted with bx in the I plus by in the j plus bz in the k. Okay, and then we dot this one over here. We have az in the k dotted with bx in the I plus by in the j plus bz in the k. Okay, it's just distribution. Now look at this product. I dot I is 1, so from that we'll get ax bx, but I dot j is 0, I dot k is 0, so that's the only term we get over here. Okay, so we get ax bx from the first line. How about from this one? J dot I is 0, j dot j is 1, so we get ay by from this one, but this one j dot k is 0, so the only term we get is ay times by. Okay, we have ay times by. How about from this line? K dot I is 0, K dot j is 0, this is only non-zero term, K dot k is 1, so we get az bz. Okay, so we have the following vector, the following formula for the dot product between 2 vectors given in the Cartesian coordinates or in terms of ijk unit vectors. You multiply the x's together, you multiply the y's together, you multiply the z's together, and then you add them together. So this is the formula for the dot product between 2 vectors expressed in the ij notation. All right, now let's consider an example. let's say A is maybe 2 in the I plus 3 in the J, maybe minus 3 in the K. Okay, let's say B is 3 in the I minus 6 in the J. Okay, so we want to calculate A dot B. The question is find A dot B. Okay, so you see we're going to multiply the X with X, the Y with the Y, the Z with the Z. If you want, you can say there's 0K over here. Okay, so the dot product is simply you multiply the X with the X, which is 2 times 3. You multiply the Y with the Y, it's 3 and negative 6. Okay, negative 6. And then you multiply the Z of A with the Z of B. That's it. So we get 6 minus 18 plus 0. We get negative 12. Okay. So when you find the dot product between two vectors expressed in the IJ notation, all you do is you multiply the x's together, you multiply the y's together, you multiply the z's together, and then you add them. Okay. Now we're going to see how we can find the angle between two vectors using dot product. Okay. Angle between vectors using dot product. Now we've seen two definitions of dot product. Okay, we have two definitions. One is the polar definition in terms of magnitude and direction, which is AB times the cosine of the angle between them. Okay, but also in terms of the Cartesian components or IJK components, we have AX, BX, AY plus BY, AY times BY plus AZ times BZ. Okay, so we have the following formula: AB times the cosine of the angle between them equals AX, BX plus AY, BY plus AZ, BZ. Okay, what that means is cosine of theta is this divided by the product of magnitudes. Okay, so you've got AX, BX, AY, BY, AZ, BZ. Okay, divided by the magnitude of A times the magnitude of B. Now remember, the magnitude of A is square root of AX squared plus AY squared plus AZ squared. The same thing about B. B is square root of BX squared plus BY squared plus BZ squared. Okay, so we have the following formula: cosine of theta equals AX BX AY BY plus AZ BZ divided by the magnitude of A, and then you multiply that by the magnitude of B. Okay, so if you know the Cartesian components of a vector, you can use this formula to calculate the angle, and of course then we'll take the inverse. So that means theta equals the cosine inverse of the whole thing. Okay, AX BX plus AY BY plus AZ BZ, and then of course we have AX squared plus AY squared plus AZ squared, and then times square root of BX squared plus BY squared plus BZ squared. Okay, so if you know the IJK components of the two vectors, you can use this formula to calculate the angle between the two vectors. Theta is angle between A and B. This is angle between A and B. between A and B. Okay. Now let's consider an example. Let's take two-dimensional vectors. Let's say A is 2i minus 3j. Let's say B is maybe 4 in the I plus let's say just j. Okay, the question is calculate the angle between A and B. Okay, so first let's calculate. We have the following. You've got AX is 2, AY is -3, BX is 4, and BY is 1. Okay, and the angle is cosine inverse of, first we're going to do the dot product, which is AX times BX. Okay, that's 2 times 4 plus AY times BY, which is -3 times 1. And then the magnitude of A is the square root of AX squared, that's 2 squared, plus -3 squared. Okay, and then we have the magnitude of B, which is 4 squared plus 1 squared. Okay, so this would be cosine inverse of, so we've got 8 minus 3 over here, which is 5, and then this is 4 plus 9, the square root of 13, and then this is 16 plus 1, which is square root of 17. Okay, so this, when you plug into your calculator, will give you the angle between A and B. Okay, now we're going to look at another kind of product. It's called the cross product. The cross product between two vectors is written as A cross B. So we use a dot for dot product and we use a cross for a cross product. Now, as I've said before, this is the area definition of a vector. Okay, let's say you have the following two vectors. Okay, the magnitude of this vector is defined to be the area of the parallelogram determined by these two vectors. There is a unique parallelogram. You take this vector on this side, let's say this is A, this is B. Okay, so the parallelogram determined by these two vectors is this one. Okay, the magnitude of this cross product is defined to be the area of this parallelogram determined by the two vectors. Okay, so how do you calculate area? Well, you take the height. Okay, let's say this is angle theta over here, and the height over here is B, the sine of theta, and then the magnitude of A times this component perpendicular to A gives you the area. Okay, so the magnitude of A cross B, A cross B would be A B sine theta. Now this quantity is a vector quantity because area has directional properties. Okay, this rectangle on this paper is not the same as the rectangle on a plane perpendicular to this paper, because the face of this parallelogram is perpendicular to the paper, but if you have another parallelogram on the surface perpendicular to this one, they'll be facing the other way. So area has directional properties. For that reason, cross product is a vector quantity. That's why we're talking about magnitude over here. So the magnitude of A cross B is the magnitude of A, the magnitude of B, times the sine of the angle between the two vectors. Okay, it is one of the vectors, the magnitude of one of the vectors, times the projection of the vector on a vector perpendicular to the other vector. And geometrically, it's simply the area of the parallelogram determined by the two vectors. All right, now let's talk about direction of a cross product. Let's talk about direction of A cross B. Okay, the direction of A cross B is always perpendicular to the plane determined by the vectors A and B. It is perpendicular. It is perpendicular to the plane determined by the two vectors. Remember, two vectors determine a plane uniquely. If you've got this vector over here, A and B, the plane determined by these two vectors is the plane of the paper. So two vectors determine a plane uniquely, and the direction of the cross product between those two vectors is defined to be perpendicular to that plane. Okay, but the problem is there are two possibilities. It could be perpendicularly out, or it could be perpendicularly in. Okay, now we should be able to distinguish between perpendicularly out and perpendicularly in. First, let me give you the symbols for perpendicularly out and perpendicularly in. Perpendicularly out is usually represented by a dot. Perpendicularly in is represented by a cross. That's because, let's say, if you look at the pen, for perpendicular, you see a dot. If it's coming out, you see a dot at the top. That's why it's talking about dot. But if you put your pen down like this, you see somewhat like a cross. That's why it's called a cross. Okay. So perpendicularly out is represented by a dot. Perpendicularly in is represented by a cross. So the direction could be either towards the paper like this, or out of the paper like this. All right. Now, there are two ways of determining the direction. They're called the screw rule and the right hand rule. So let's look at these two rules. Let's look at the screw rule. The screw rule. In this rule, what you do is, let's say you have the two vectors over here. This is A, this is B. You put a screw over here perpendicular to the plane determined by the two vectors. And then you rotate from the first vector to the second vector. That is, if you're doing A cross B, you rotate from here to here if you're doing A cross B, okay? And if you're doing B cross A, you rotate from B towards A, okay? So for A cross B, you rotate the screw from A towards B, okay? So the rule is, put the screw at the intersection of their tails, perpendicularly, okay? And then rotate the screw from the first to the second vector. That's important. Let's say A comes first, you rotate from A towards B. If you're doing A cross B, you rotate from A towards B. But if you're doing B cross A, you rotate from B towards A. Okay, so this is important over here. All right, then the direction of movement of the screw gives you the direction of the cross product. Then the direction of movement of the screw gives you the direction of the cross product. The direction of the cross product. Now remember, a screw goes in when turned clockwise, it goes out when turned counterclockwise. Okay, a screw goes in for clockwise, goes out for counterclockwise. Okay, now let's look over here. If you're looking for A cross B, you put your screw over here like this, then you rotate towards B, that the screw comes out or goes in. You see, I'm turning counterclockwise, the screw comes out, so the direction will be perpendicularly in. So if I'm doing A cross B, I will rotate from A towards B, that is counterclockwise. For counterclockwise, the spring goes out, so the direction would be perpendicularly out, or you can represent by that. How about if I do B cross A? You see, you rotate from the first to the second, so the first is now is B, the second one is A. Now we'll go this way from B towards A. Okay, that is clockwise, so the screw will go in. Okay, so the direction will be perpendicularly in. So for this one, the direction will be perpendicularly in or across. The reason is this is counterclockwise, and this is clockwise. Okay, so that's how we determine the direction of the cross product using a screw. You put the screw at the intersection point of the two vectors perpendicularly, and then you rotate the screw from the first to the second. Okay, then the direction of movement of the screw is the direction of the cross product. If the screw turns counterclockwise, it comes out. If the screw is turned clockwise, it goes in. Okay, so we see that cross product is not commutative. If you change the order, the vector becomes the negative. Okay, so we have the following property of cross product. If you flip the order, it doesn't remain the same. It becomes negative B cross A. That means cross product is not commutative. Cross product is not commutative. Okay, all right, now let's see at the other rule. It's called the right hand rule. Right hand rule. Okay, so in this case, let's say again we have the vectors B and A. Okay, first you align the vectors A and B. The first vector is aligned in the direction of the index finger, and the second vector is aligned in the direction of the middle finger. Okay, so first align the index finger in the direction of the first vector, in the direction of the first vector, and the middle finger, in the direction of the second vector, in the direction of the second vector. And then align the thumb in a direction perpendicular to both fingers. Okay, just like this. This is the first vector, second vector, like this. Then the direction of the thumb represents the direction of the cross product. Then the direction of thumb represents the direction of the cross product, the direction of the cross product. Okay, now let's look over here. This is the index finger, so I align the index finger in the direction of A and the middle finger in the direction of B, and then you see the thumb points up. Okay, so if I'm doing A cross B, this will be perpendicularly out. Okay, because to do that, this index finger this way, middle finger this way, this should point up. But if I'm doing B cross A, I can do like this. I have to do like this. This should be B. Now B is the first vector, so the index should be in the direction of B, the middle finger should be in the direction of A, so the thumb points down. Okay, so this would be perpendicularly in. Okay, so that's how you do the direction of cross product using the right hand rule. All right, so there are two rules, the screw rule and the right hand rule. I personally prefer the screw rule, but a lot of people like the right hand rule. All right, now let's look at some properties of a cross product. Some properties of a cross product. Now, what do you think you'll get if you cross product a vector with itself? Okay, what's the angle between two identical vectors? You see, identical vectors, the angle will be 0. Okay, theta would be 0 for two identical vectors. So this would be the magnitude of A cross A equals A times the sign of 0, which is 0. Okay, so we have A cross A. If you cross a vector by itself, you get 0. Okay. Well, we have a recent second property. If you flip the direction, it becomes negative. Okay, negative B cross A. If you reverse the order, you get the negative. Okay, so cross product is not commutative, commutative. Okay, and the other property is cross product is distributive over addition. Okay, if you've got A cross B plus C, you can expand it. This equals A cross B plus A cross C. That is, it is distributive over addition. Distributive over addition. Just like normal multiplication. This is the only odd property. If you flip the two vectors, you get the negative, not like any normal multiplication. All right, let's consider an example. Let's say we have the following vectors. Let's say A is maybe 10 meters, let's say 30 degree north of east. Okay, and let's say B is 60 degree, let's say maybe 20 meters 60 degree west of north. Okay, so the question is find A cross B. Find A cross B. Okay, so let's draw the vectors. So that's what we have. The first vector is 10 meters. Let's use the scale 1 centimeter per 10 meters. So this would be this vector at an angle of 30 degree. We got 10 over here. And then the other one is 60 degree west of north. This is north, so we go 60 degree this way. This is 60 degree over here. all right? And that's vector B, okay? First, let's do the magnitude. The magnitude is, okay, like this. It is A, B, the sine of theta. So obviously we have A equals 10, B equals 20. How about the angle? The angle is, we have 60 degree over here plus another 60 degree, 120 degrees, okay? So theta is 120 degrees, all right? So the magnitude of A cross B is 10 times 20 times the sine of 120, okay? So we have the sine of 120, this is 30 degree over here, this is 30 degree over here, so we're talking about the sine of this angle, it would be this part over here, okay, which is given by cosine of 60. So it should be about this times about 0.86. Okay, this 100 is 20. So this side is the sine of 60. Okay, so it should be times about 0.86 over here. That is 19.6, maybe 196, and so on. Okay, so that is the magnitude. All right. All right. How about the direction? The direction, we got these two vectors over here. This is RA, this is RB. So we're going to rotate, let's say put a screw over here. You rotate it from here in this direction. That is a counterclockwise direction, so it's going to be perpendicularly out. Okay, perpendicularly out, or a dot. Okay. All right. Next, we're going to see how to obtain the cross product of vectors expressed in the IJK notation. Okay. Cross product of vectors expressed in the IJK notation. IJK notation. Okay. Before you do that, we're going to look at the cross product between unit vectors. So what happens if you cross I with I? Okay. The angle between I and I is 0, right? So magnitude is 1 for both of them, and then you've got the sine of 0. The sine of 0, which is 0. So generally, if you cross product a vector by itself, you get 0. You get 0. Okay? How about if I cross a vector with J? Okay? Let's say you have this system over here. Let's say this is I, this is J, this is K. Okay? I cross J means you put your screw over here and you rotate this way. That's counterclockwise, it goes up. That's in the K direction. Okay? If you flip it, it becomes clockwise and you get negative K. Okay? How about if you're doing J and K? Okay, let's say J cross it with K. Okay? You would go from J towards K. Okay? You see, put your screw like this. Again, you're going counterclockwise. It's going to be perpendicularly out, but the direction perpendicular to this plane K and J is I. Okay, so you get I. But if you flip them, you get negative I because it becomes clockwise. Okay? How about K cross I? k cross I. Okay, so you're going to put your screw over here. You can rotate from k towards I. That is counterclockwise, and the perpendicular direction is j, so you get j. And if you flip them, that is I cross k, you get negative j. Okay, so you might think this is very difficult to remember, but there is an easy way for remembering. Let's say we have this unit circle over here. Let's say we have I over here, j over here, k over here. Now if you do I cross j, if this direction is counterclockwise, you get the, when you do the cross product, you usually get the other vector. Okay, all trying to figure out whether it's positive or negative. So if you do I cross j, that is counterclockwise, you get positive k. But for j cross I, that's going to be clockwise, so you get negative k. Okay, when you do k and j, the vector is going to be I, but if you do j cross k, you go counterclockwise, so you get positive I. But if you do k cross j, you go clockwise, you get negative I. Okay, the same thing about from k to j. From k to j, you go clockwise, so you get positive j. But if you go from I to k, that's clockwise, you get negative I. So this is the easier way of remembering it. Just remember, when you cross two unit vectors, it's usually the other vector. The question is it positive or negative? And using this circle, you can easily determine it's positive or negative. Okay, so with this cross product of unit vectors, now we can do cross product of vectors crossed in the IJK notation. All right, so let's say we have the following vectors. A is AX in the I plus AY in the J plus AZ in the K. B is BX in the I plus BY in the J plus BZ in the K. Okay, so for A cross B, we have the following. We have this vector plus AY in the J plus AZ in the K crossed by BX in the I plus BY in the J plus BZ in the K. Okay, now we're going to distribute. We're going to cross this with B. Okay, BX in the I plus BY in the J plus BZ in the K. And then we'll cross this one, this plus AY in the J, cross it with BX in the I plus BY in the J plus BZ in the K. Okay, and then plus AZ in the K, cross it with BX in the I plus BY in the J plus BZ in the K. Okay, all right, now let's do the first line. I cross I is 0, so we don't have to consider this one. But look, I cross J is K. Okay, so from these two we get AX BY in the K. Okay, how about between these two? IK, you see, to go from I to K, that's clockwise, so we get negative. So we have minus and minus AX BZ, and that's in the J. Okay, now let's do the second line. J cross I, you see, is clockwise, so it's going to be negative K. Okay, so we have AY BX in the negative K direction. Okay, because from J to I is clockwise. Okay, now J cross J is 0. Now we have J cross K, that's I. Okay, so we have plus AY BZ in the I direction. Okay, now let's do this one. K cross I is counterclockwise, so we get AZ BX J. Okay, K cross J. K cross J is in a clockwise direction, so we get negative. AZ, BY, where KJ is going to be I. Okay, and K cross K is 0. All right, so we're going to put the I's together and the J's together. Okay, so let's do the I part. The I part, we have this one and this one. Okay, we have AY BZ minus AZ BY. And now let's do the J part. We have this J part and this J part over here. Okay, we got these two. So this is AZ BX in the J, and then we have another one, AX BZ. Okay, and then the K part, we have two K's, this one and the other one is this one. Okay, so you've got AX BY, and then the second one is minus AY BX. AY BX. Okay, you might think this is difficult to remember, but look, this is I, which is the X part. You see X, Y, Z. Y going in a counterclockwise direction. After Y comes Z, after that X, and this Z, after Z comes X and then Y. Okay, so it's very easy to remember. This is in order: X, Y, Z, Y, Z, X, Z, X, Y. That is in a counterclockwise direction. For the second one, you just flip this to Y, Z, Z, Y, Z, X, X, Z, X, Y, X, Z. So you see, this is the IJ this is a formula for the cross product of two vectors expressed in the IJK notation. Okay, remember, there's an easy way for remembering this one. This is I, which is last X, the next one is Y, BZ. So in order, you see, over here you just flip them. Over here you got Y, the next one is Z, X. Okay, and over here you just flip them. This is Z, after Z comes X if you're going in a counterclockwise direction, so you've got Z, X, Y, and then you flip them. Okay, so this is the IJK formula of a cross product. Now, if you're familiar with determinants, there's another way of doing it, using determinants. Using determinants. You can write, if you expand this determinant, let's say you start with I, J, K, and then you put the first vector over here and the second vector over here, and you expand this determinant, will be equal to the expression that we just got. Okay, so if you expand this, it will be exactly the same like the formula we got. Okay, if you remember the expansion for this one, you start with I, okay, and then you take this off, and then you will have AY BY AZ BZ. Okay, the next term is negative, if you remember the formula for expansion of determinants, and then you will take this one off, that's the J, you get AX AZ, and then BX BZ, right? And then you take the K part, you take this one off, you get AX AY BX BY. Okay, now if you expand this, you get, you see, the determinant, this one is the product of the minus this product, right? So you got AY BZ minus AZ BY, and then the J part would be this one, AX BZ minus this product, BX AZ. Okay, and then the K part, you have this AX BY minus AY BX. Okay, now let's turn it into a positive by flipping these two, so you get the following. So this A cross B, you get the following. A cross B equals, the I part is AY BZ minus AZ BY. The J part, I'm going to make this positive, and then I'm going to flip these two. So you've got AZ BX minus AX BZ, and then plus K is AX BY minus AY BX, which is identical to the formula that we just obtained, right? So if you're very familiar with determinant, you know, for some of you, it may be easier to expand the cross product using this formula. All right. Now, we're going to look at finding angle from a cross product. Angle between two vectors from a cross product. Okay, so we have looked at two definitions for cross product. Okay, so we have, this is, the first one was the magnitude of A cross product equals A times B times sine of theta. Okay, but we can also obtain the magnitude of the cross product from this formula, okay, which is the square root of this expressions over here. All right, and so we can also say this equals square root of the x part, the first part, which is AY BZ minus AZ BY square root, okay, and then we have the second term, which is this one over here, AZ BX, AZ BX minus AX BZ, and then the other one, the third term, would be AX BY, AX BY minus AY BX, okay, so squared. So this will give you the magnitude. Therefore, you can say the sine of theta equals, let's just say the magnitude of A cross B from Cartesian coordinates over here, divided by A times B. Okay, so if you can obtain the magnitude of the cross product from here, you can calculate the sine of the angle. Then theta equals sine inverse of the magnitude of A cross B, which you can obtain from this formula over here, divided by the magnitude of A and the magnitude of B. Okay, so that's another way for calculating the angle between two vectors.